Alright, time for another draft physics video presentation. Where to begin? Just thought I'd go over some of the simple basic stuff of physics and explain an overview. Some of the overview anyway. See where it goes. Just begin with the beginning. The statements that probably could have been made by somebody like Aristotle or whatever, observations that are so fundamental, so elemental, that they should always be kept in mind. They should always be, in your head saying, keep in mind that, always remember. And physics has lost track of all that kind of stuff, just like they've lost track of their whole scientific method, voodoo rules, where they, pretend they don't need to repeat experiments anymore, and they don't have to be careful, and they don't have to do the controls, and they don't have to, they don't have to do a lot of things before they can say they proved something. They don't have to compile evidence, they just have to tell good stories. It's all about a good storytelling. It's, saying your story and having good animations and blah, blah, blah. So I guess the first thing I'll just say is, somebody knows of some video out there, professor, lecture, interview, talking head stuff, documentary, that actually does physics something like with any kind of integrity, that isn't just bullshit. Or anyway, just thinks that it's just so good an argument that I couldn't possibly show how it's crap. Yes, please link to it. Please link to this physics done right. Especially on subjects like magnetism or something. As they all go crooked. Anyway, can't find anybody near the truth there. So, even among the dissidents, it's all bullshit. Nobody has any respect for straight lines. See, that's one of the things I like to talk about. Straight lines. Yeah. How it's so much more elemental than a crooked line. This is just basic stuff. So first, there was somebody who commented about what operating system I use, and so I just thought I would, somebody answered the question. It's Linux Mint Cinnamon, I think. Anyway, some version of it. And the problem is with, I'd love to be a Linux fan, and push it and all that kind of crap and do more videos on it and all that. But the truth is, you do have to fiddle with it to get it to do anything. Like, if all you want to do is browse the internet, fine. It's a great operating system. It loads fast, runs on almost anything, and it does that basic job of connect to the internet and get a browser running. But if you try to do anything more complicated, I ran into all kinds of problems in the sense of being able to get software that could do, a decent frame rate of my video. Well, if I run the program that can do that, it wipes out my hard drive because of a glitch in some other, files that are temporary files that it uses that somehow the operating system can't deal with. So it's not like the program's fault, it's the operating system's fault, but, the point is that you have to do something about it. So you have to write another little piece of code to wipe out those files, and, so there's all these little things that you have to tweak it to get it to run. So you can't really just suggest to somebody, oh yeah, run Linux. Because, you probably will have some problems that are going to be specific to your computer and its hardware, and you have to deal with all that little crap, and you have to try to figure it out. And there's no real good way to figure it out because, millions of people, billions of people, millions anyway, are supposed to be using this operating system, but it seems like nobody uses it for anything because every single problem I've had, the solutions are, 10 years old or non-existent. It's like nobody else has had that problem kind of thing. You're like, come on, get real. It's obvious this is a problem. And somebody must have encountered it. But anyway, it's not very good. So, that's all I have to say about that. I'm doing fine. Been using Linux now for, 5 years or something. And I don't have any major complaint except for the fact that, yes, you sometimes have to do a lot of work to get it to run right. Even now, I have to still reboot before I do videos. It's not a real big problem because it only takes 40 seconds to actually go from hitting the restart button to actually being able to reload what I want to reload. And that's the other problem, though. It doesn't restore what you previously had open. So it's not, but as long as you keep that simple, it's not a big deal. So it's not a big deal at all. But if I don't do it, if I make another video without, let me put it this way: if I suspend and then make a video later, that won't work. So it'll crash. The video will stall in the middle somewhere and waste my time. But I'm just saying these are all the little subtleties you have to, workarounds you have to deal with. And so anyway, just commentary for those who might be interested. Sorry for those who aren't. so anyway, so getting to the first argument, which is that's a little bit. I get a better chair than this 1943 shit chair. But anyway, different things I have to work on. No an issue. Alright, so that's a little better. Where did I put my chalk? There it is. Okay, the first thing I've argued is that, you look at the universe and what could you observe? This is like an Aristotle kind of thing, like thousands of years ago they could have kind of figured out this push-pull thing. So, I'm arguing that this was a big deal, kind of like in my perspective, was understanding that, this push-pull, there is a huge asymmetry between these two concepts of a push and a pull. The push is so simple, you can think of just a million ways you can push something. It's just this idea of something comes from somewhere, hits something, and the something has to react because it got hit, and so the push is just so obvious. And the pull is just so impossible to do in any kind of elemental way. There's no simple pull. And even if I contrive some kind of pull machine, I'm still stuck with the idea that I have to have something reach out and grab something and essentially push it. So I'm still stuck with the idea that the push is elemental and the pull is emergent. There is no such thing, in fact, that every single pull will involve reaching around essentially and pushing on something. I can't really pull anything without grabbing something, and when I grab it, what am I doing? I'm creating the ability to push it. That's the whole point of grabbing it. So, and this is, once you know that, okay, once you say, okay, I get that, that's a truth, right? Now, I don't think anybody can deny that, right? I mean, it's just like it's as solid as water is wet. We invented words, and this is the only way you could deal with it. And so it's like, nobody can really rationally argue this one down and say, oh no, pull is more elemental. The tractor beam or something, creating some kind of mechanism where you can have low pressure on the inside and somehow you don't have to have higher pressure on the outside for it to be pushed. Like there's no conceivable. The only reason why a vacuum works is because, a vacuum puts the pressure on the outside, right? I mean, it's kind of obvious. It's pushing. The outside pushes the whatever into the vacuum. So, and I just say that everything about physics today is obnoxious to this observation. I mean, it hates this observation. This observation means nothing to it. The fact that there's this huge, not the same. These are not inverses of each other. These are not plus and minus. These are not blue and red. These are not black and white. These are not in any way equal words. There's no sort of equal. I don't even know how to, same thing, just a little different. No, this is the universe. Push is everything. And I guess I could argue this is sort of like pain and pleasure, and if you want to make a comparable philosophical argument, that which one comes first? Well, the ouch comes first, the negative. And everything else is the relief of the negative. You don't have the negative, you have the byproduct of not having the negative is, hey, I feel pretty good. just getting rid of the bad feelings is 99.9999% of the job, so to speak. But it's a little bit, that's philosophy, a little more complex than argument. But I'm just saying, this is where you start. So you start looking for where things are bumping into other things, pushing them. You don't bother even thinking about this idea of something pulling on something. It's just kind of a nonsense idea. Just isn't going to work. All right, so on the next level, you have the speed of light. And as I pointed out, no, it's the speed of force, right? It's force that forces, that have this quality of moving the speed of light. All the mechanisms that create pushes that we don't see, all the invisible pushes move at the speed of light. So magnetism and electricity, virtually the speed of light. Light, right? Light moves the speed of light, and gravity moves the speed of light. That's their theory. They understand that. They sort of agree with those basic notions. And these are all forces. These are all these little bits, the stuff that we can't see. The devices we're saying are doing this pulling thing, which is nonsense, but that's the thing doing the pushing. That there seems to be the two things in the universe, right? And so, and then what do we know about this stuff that's moving the speed of light? The speed of force. See, just a simple change. Focus on push and recognize it's not the speed of light, it's the speed of force. It's the speed of all the little crap, moving the speed of light. All of those things. And that's what it should be called, the speed of force. It's not just light that moves that speed. It's these other things that move that speed. And therefore, we should understand that as a concept, as a thing, not as if it's some force is some variant of light. It's that light is a variant of force. And so that's another simple thing. You're just saying, come on, they should be able to handle that. And what's the trick though? The trick with force is that you can't bang a force into a force. So if the universe was just made out of force, that is, if we said it was quantized, that's an important concept. It's the idea that it's in little chunks. Maybe you could get along with that idea. Maybe you could talk to a conventional physicist and you said, okay, it's in little chunks, it's in little Planck bits, little, you can reduce it, and that's as far as you reduce it. It doesn't reduce any further. That there is such a thing as elemental, and you can't go any. There's no internal mechanism smaller. There's no, it is what it is, and that's all that it is. It's that simple. It's so simple you can't make it any simpler. And so the idea would be that you have this little quanta, this little piece of this force stuff, and this force stuff doesn't appear to be able to interact with other force. So I can't take two bits of this force by itself and make it do something interesting in the universe. Now maybe the rule is that it always just, whatever it does, it always looks the same. Two things hit each other, two things reflect. It looks the same as if the two things missed each other, right? You'd end up with an arrow going this way and an arrow going that way. So maybe that's the reasoning. But the point is that you can't change anything. The universe can't evolve. It can't do anything that you could notice. Nothing can change, if force is all you have. So there has to be something else for the force to interact with. Force won't interact with force. You can't push a pusher against a pusher. The little bits moving the speed of light stuff can't do anything. They need something called matter. And we know that you can convert matter as a concept into understanding that it's made of something. Like you could say atom, they were very clever. When you think thousands of years ago, they were already figuring out we might be made out of little pieces, little bits. But they didn't take it that, they couldn't take it that step further to understand that, well, yeah, we can dissect the atom bit into some idea of understanding what a proton and an electron are. And this is something conventional physics already knows, that the neutron, okay, decays into that. So this is a composite particle, and you can really understand it as just being electrons and protons. So that's all you have. Let's just make a distinction between them. You have the little thing called a negative charge and a positive charge, and they have this inverse relationship. What if this one is in a place in the universe that's causing it to go, the electron's here, and it's in the universe, and the universe is telling it to go this way. Well, if I just switch it and put a proton there, the universe will be telling it to go that way. And so they have this inverse reaction to any place you put them. Whatever the electron does, the proton will do exactly the opposite. It's that, it's kind of that simple. So whatever's affecting matter, the distinction is that somehow you have to create an idea or a mechanism that can create this inverse reaction, that there's an exactly opposite reaction to what's happening. That somehow if you're hitting the electron with wet, somehow the proton's perceiving it as dry. You're saying, come here, it's saying, I'm going, the proton says, I'm going away. It's just this weird inverse relationship. And so that's a little bit mysterious, yes. All right, so we'll get rid of the neutron because you don't need that. But yeah, so matter's just protons and electrons. It's just the positive charges that are really the negative ones, right? Well, whatever. Should be labeled back the other way. And it really doesn't, the plus and the minus is only relevant because when you use electricity, you're adding electrons or subtracting electrons, and that's where the minus becomes important, because adding electrons shouldn't be called making more minus. It would be better if it was called making more plus. But anyway, so the real game is this stuff moving the speed of light, the little quanta force bits. So if you just understand that the force, okay, another thing about the force, so I should have, this is really important. What we can observe about force is that if you're at all careful in observing forces, you can understand that they travel in dead straight lines, okay, on their own in the universe. That there's forces are not wacky on their own, okay, by themselves, left to their own devices, so to speak, going from here to there, blah blah blah. Unless you put something, matter, to mess with them, they will just do this. They'll go from point A to point B, okay, in a straight line, and they'll do it at this set speed. And that's what they do, okay? They don't do anything else. They don't go over here for a little while and then come down here and go over there and do any waving stuff or do any turning on and off or any of that stuff. They clearly, whatever they are, even if you want to think of the universe as being made of some ether crap, well, I don't know why you would do that, but whatever. You want to think of it as, things pushing on other things, and so one thing gets pushed and the push goes to here and then push, a bunch of dominoes. The path natively is straight, okay? There is no, I feel like going this way, or, I'll go this way and then I'll go this way and then I'll go over it. No, there's none of that. And you can see it if you look for it in all of the established physics. They just don't pay any attention to that part. So, when they want to demonstrate something, they'll show you an equation instead of showing maybe Maxwell's drawings, right? So, of charge, but that's a good example, that charges function. The inverse square law is pretty much a byproduct of the fact that the force is, okay, straight line, that it always comes perpendicular off the surface, and it creates an equidistant, an equal field, okay, around it, that also just creates like a new surface. At this surface, the gravity is 10 meters per second. At this surface, it's going to be 2.5 meters per second. all the way around. It's the same distance. And the force, has to spread into more space, with a spherical object, in both dimensions. So it's diluting. It's going into more space, so therefore it's diluting by that perception, by this arrow's getting weaker and weaker in terms of how much space it has to fill, so to speak. But anyway, there's lots of mechanical in their math. This is Gaussian. This is fundamental to their own math. They know this principle, and yet they completely lose it when it comes to something like magnetism. They start drawing a bunch of these kinds of lines. They start drawing a bunch of crooked lines and thinking these crooked lines have something to do with anything. And those are the same crooked lines you get by doing this with two charges. So if I have two charges interacting with each other, you can still see this, right? Yeah. The two charges will be doing this nice straight line thing if they're far enough away. Everything will be nice and straight and spherical and symmetrical. The force is being essentially created by the idea of understanding rays coming out of the thing, and that the rays have a density that's proportional, and it'll get hit by a certain amount of rays. The further away you go, the fewer rays that'll hit you, and it's all perfectly logical, right? I mean, there's this diverging lines that essentially are establishing the strength of what you're going to get hit by, how many of these lines you intersect. This is a key part of their mathematics, is just counting how many lines. You just have 10 lines represent a million lines, and you just count how many lines you're intersecting, and you can figure out exactly how strong the force is. So they know all of this, and then they know when the two charges mix that I'm going to start getting lines that are going to look a little bit funky, okay? Because those are going to be the lines where the force is equal. And obviously I'm not going to have an equal amount of force in all these locations, so my lines are going to start getting weird shaped because I'm really taking a vector from one place and a vector from another place. And they know this too. They know this is Maxwell. You just combine these two vectors, okay, to decide where the new line is going to be. And it'll be stronger force from one object, weaker force from the other, and this will be a new location, and you'll create some kind of weird shape that encompasses the two objects. But the weird shape was created by straight lines from the object. No matter where I put something, it'll be straight lines from the objects that are creating those lines. So they know this, but that's where it all goes wrong, because that fundamental idea, okay, that simple idea, okay, so we're just saying these are the simple rules here, right? That we have a push universe, that matter is forced, okay? It's not like space tells matter what to do. No, force tells matter what to do, okay? Force moves matter. By moving the matter, you move how the force is going to bang off of it, and where the light's going to hit me. I move closer to the light bulb, more radiation hits me, more radiation hits the stuff in the room. It reflects off me. There's a consequence to my matter moving to other things, because the force is going to now reflect or transmit or do whatever, interact with me differently, and they're going to see something different. They're going to be hit by something different because I changed my position. So that simple concept that matter is forced into new positions, the new position kind of screws up the force. That's the interaction. That's where change comes from. So that's just as a simple, and the idea that, god damn, straight lines, this is elemental. A straight line, you can't get any more elemental. This is how the thing works. It's straight line force. The force never, unless you fiddle with it, unless I make it hit a piece of matter. Okay, when I make it hit a piece of matter, the force could go here. The force could go here, depending on how it interacts with whatever the matter is. And it's going to change the world. The universe changes because I had the force interact with a piece of matter. The matter goes to a new position. Now the matter is going to react. But I'm just saying these three things. Just this idea of push, that there's only two players in this game. There's the forces, okay, the stuff moving the speed of light that bounces between things. that you can reflect off a mirror. For LIGO, for example, the light reflecting back and forth in a mirror. The force is there. It's moving. It's hitting. It's bouncing back and forth. Come on. Not complicated. That there's force and there's matter, and the matter is just electrons and protons are the only meaningful players. All the rest of their fancy bullshit particles are all composites, and they all degrade. They all don't have any stability at all. So they're all imaginary nothing almost. So they have no life. They have no place in the diagram of their atoms even. They don't draw antiparticles in their atoms. They don't draw, all these tau muons and neutrino electrons and all this other crap that they say exists. It doesn't play any real role. This is all there is. There's negative charge, there's positive charge, there's force. Now, I've already explained that the simple solution is the 2 plus 2 physics, 2 plus 2 plus 2, okay, physics. That all you need to understand is there's two kinds of force. That's why there's an inverse action between electrons and protons. Because there's two kinds of force. There's two kinds of matter, electron, protons, plus, minus. And there's two kinds of interactions. There's the interaction where it pushes directly. That is, this comes in, this thing goes this way, and that's it. Not complicated. And there's a more complex interaction where this comes in, and if it's the wrong force, the electron force hitting a proton, for example, well, the proton goes this way and the reflection goes this way. So this thing moves a little bit this way, and this thing moves, the force reflects out this way. That's the consequence. So it causes a little bit of a jitter sideways instead of momentum this way, acquiring momentum that way. All right, so, and that's all you need. So all you need is, understanding that there's two kinds of force. We could say red and blue. And when you mix red and blue, you get purple. And that explains magnets. Magnets just see purple coming in. They're able to convert the purple into blue coming out one end and red coming out the other end. And, but it's always pushing. There's never anything pulled by anything. And in the case of gravity, well, it's all purple. The magnetic component is almost irrelevant. It's so weak. And it's really just about the fact that, the fact is that when you're, well, I don't want to really do the gravity theory here, but the point is that when you are moving something, when something moves towards something, it's absorbing force that can't get to it anymore. So when I move, I'm absorbing a force that would have hit you. So when I'm occupying a force by moving, that means the force isn't going quite the speed of light anymore, and it's not going to get to you in the same amount of time it would have before. So now there's an opportunity, all right, for that lack of force to be a reality for you and cause a vacuum, so to speak, an absence of push. All right, so I'm getting pushed more from one side behind me than I am getting pushed in front of me, and therefore I'll end up moving in that direction. So all you need is a slight difference between the speed at which the force moves and the speed at which the matter moves, and any difference will create the energy, so to speak, the change in push on one side of you than the other side of you, and you will move. And when you move, what are you going to do? You're going to do the same thing. You're going to absorb a force that would have hit me, so to speak, when you move towards me, and therefore I can't get hit by that force, blah, blah, blah. But the point is that interaction happens, but you fall into gravity being created by the matter that's already doing that in the Earth. The Earth has already got stuff moving this way and stuff moving that way. And from your perspective, the only stuff you can see, the only stuff that matters to you is the stuff moving towards you that doesn't get to you. The stuff that's moving away from you that doesn't get to Pluto, you couldn't care less. You can't see that. You can only see the stuff that would have hit you and isn't. That's a difference. What difference it happens to Pluto, it just isn't going to matter to you. Alright, anyway, you're not going to be noticing that. Well, anyway, I didn't want to get into the specifics. I just wanted to do this outline part. So it's just this simple idea of push. That force is pushing matter, not space, not magical things, not invisible things, not fields of nothing. The fields are made out of this force. There's no field without the force being in it. The quantas of force, the bits of it. That's why the field can have an intensity. It's because it's the amount of stuff in it. Okay, can have a lot of stuff or a little bit of stuff. It can be mostly red or mostly blue, or and it's all you're doing. That's the field. The field is the soldiers. The field, the waves, whatever you want to think about it as, have to be made of something. It's a quantity of something, and that's the only rational way to look at it, in my opinion. I mean, it's just this is too simple. So you have straight lines, very elemental. Can't get any more simple than a straight line. Right? There's just no simpler mechanism. So why not stick with the simple one? Why not explain the universe with the simple mechanism rather than the complex one? Because you can. It does work. It does add up. It's right there to be understood. So anyway, this is stuff they pay no attention to push. They pay no attention to the fact that we sort of know that there's these two things. They're world of fields that are really worlds of forces, right? We can say it, right? I can say that, and you should be able to agree, even if you hate my physics or hate me. You should be able to agree that the word force is symmetrical, is same as this whole idea of a field. A field has force in it. A field moves at a speed, and the density of the field is essentially something that could be called a force. So why are we playing this game? So we know that these fields are one thing and the matter is another thing, and that you don't need all these extra neutrinos and other bullshit particles. All you really need is the real players, which are the plus and minus ones, which are creating the polarity, and the polarity creates magnets and electricity. So that one's already tied together. Maxwell already showed you that magnetism and electricity are just versions of the same thing. I mean, I could argue to you that photons, okay, one of the forces, is electricity. Okay, electricity is just photons inside the wire. It's the same idea. It's the same little bits of force, little quanta of force pushing stuff. And that's it. So it's not even a complex conversion. And it happens. You know that light has this ability to create electricity when you put it in the right thing. And you could understand that there could be substances where the electricity travels in a nice, goes from point A to point B, goes from the plus end to the minus end. And you could have materials where, it goes here and it goes swirling over here and it swirls, where it dissipates in the object. So much like sound, you could have you can have a situation where you can move something and there's no sound. And then you can have a situation where you move it fast enough, there is a sound. Okay, that somehow it's just the way the force decides whether or not there's just a bunch of heat rather than something else, like a transmission. Something to take the straight line from point A to point B, or a bunch of crooked lines, that end up going nowhere and just end up converting it to energy lost in some direction that you won't be able to see. Just like if I take a light bulb and I push all the photons together into one stream, I have a very intense laser. But if I disperse them, I have something that I won't be able to feel, because they're going places that aren't going to hit me. They're not going to hit me in one location. It's going to be hot enough. Just like focusing photons with a lens. A lens just means, it's how much energy is hitting the surface of the lens. So that much photon, right? So I could have a lens and just say, well, that I could be sitting in the sun and say, well, how come that 2.5 inches of lens isn't burning me? Well, because it's not, all the photons aren't being shot to one location, one tiny little spot. But if I shoot them all to one tiny little spot, I'll burn a hole through me. It's kind of, this is easy to understand kind of stuff. This is the elemental universe. All right, so I will go to the, I'll just throw in some of the new observation, the simplification I've made on understanding how force and matter interact. And so what we can observe is that if there's some kind of system, like the force is doing something specific. It's not, the push isn't just, well, it is just, it's that simple. I had it more complicated. The idea is that we know that this matter has something called momentum, but we can't see it, right? So we can't see electrons and protons. But we have this idea that they get hit by the force and then they gain momentum and they can just keep going forever. And that's the perception. That there's some, like, the little bit hits and somehow it exchanges this movement power. But you have to kind of understand that, photons don't hit something and then stop, and like the kinetic, like Newton's cradle. Okay, you can't just make one ball stop and the other ball move. Now, that makes sense. That's the way it works. You have to have this conservation of energy. But, this little bits, well, when you really think about what they're doing, it doesn't work, mechanically, because this little bit of energy can't possibly stop. So that can't be happening. So what's really happening? I mean, the little bit can't go off reflecting this way and this thing go this way without there being something, some other price you paid for that, some other exchange to make the conservation, so you're conserving movement. Because the force is moving, and you have to somehow move another force. And so then you get into Newton's observation about, something keeps moving until you act on it with an equal and opposite force. You apply a force, the thing moves, and then you have to apply an equal and opposite force to stop it from moving. And then there's the whole point of reversing its motion, which is sort of the perception. But anyway, so the idea is that I had to come up with some, in thinking about it, some way you can make this transfer. And so the idea is that, okay, the bit goes inside the thing, the quanta of energy, the little force bit, and that's where it makes this exchange. It just, one bit stays in, one bit pops out, so you have an equal mechanism that, you haven't broken conservation. Okay, you're just saying that this thing is trapping energy, and that it can, as long as it gives one, as long as a rower, I use the analogy of a rowboat. Rower goes in, one rower has to leave. There's only a certain number of seats, and then the boat goes wherever the collection of rowers is going, and it works, but it's more complicated than you need. So you can make it even simpler in terms of understanding. So what I'm arguing now is that when an electron, let's say, and it's electron force, so we're just going to use the one force for this example, gets hit by a force, what actually happens is that force stays with the electron, and the electron will move to a location. So if this little bit was going this way and it hits, and the electron doesn't have another bit on it, so let's just say the electron is clean, nothing else has ever hit it. This is the first piece of quanta to ever hit it. It comes in and it sticks. And what it's going to do is the electron is going to go with it. Like the electron's a balloon. And it's just going to, it doesn't weigh anything. It doesn't slow it down much. Let's say it just slows it down a little bit, and it goes only 3/4 of the speed of light. So it slows it down a little bit because it's got some mass. So it has to, this little quanta has to push this thing. And the two would just, this lacks momentum. This has momentum, but this has some drag. Let's just say natural drag. Well, anyway, it doesn't really matter, but I'm just saying, just think of it as the energy hits it, and that's which way this thing goes now. Okay, the energy was going this way, it sticks. This thing now, like Velcro, it just sticks. Now the trick is, if a new piece of energy hits, say from this direction, what's going to happen is this thing's going to stop. Okay, and what's going to happen is both of these things, okay, now are going to interact with each other, so to speak. The matter is just going to be a conduit for the force to bang into each other. They can't do it until there's the piece of matter to allow it, so to speak. And now, so what's going to happen now is both of these things are going to reflect, and the reflection will be a composite of the two vectors. You have this way, and then you're adding this way, and so your reflections will be this way. The bits that fly off will fly off this way and that way, let's say. And now the electron goes back to being nothing stuck to it. So every time there's an interaction, all that's really going to happen is these little bits of energy are going to go from a position where there's something stuck on it to nothing being stuck on it. And something, nothing, something, nothing. So the electron goes through space, basically, just being caused, it's probably not the best way to draw it, to move, but it doesn't move consistently. So the electron just basically moves a bit at a time. Okay, it stops, it goes, then it stops, then it goes, then it stops, then it goes, then it stops. Alright, it does that in directions, depending on what hits it when it's stopped. And I sort of explained this as a little bucket thing. I've done this many times, but if you put energy into the front end of the bucket and the energy is frictionless and it just goes back and forth, 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 you could sort of understand that the little box would end up rolling, and then it would stop when the energy hits the back end, right? And then when the energy is moving forward, when it hits the front end, it'll go again. Okay, so it stops, then it goes, then it stops, then it goes, then it stops, then it goes. And it's a way of understanding how you can trap energy and trap motion, perpetual motion. So you'll keep going, it's just that you don't go constantly. You stop and then go, and then stop and go, and stop and go. So anyway, so you have to kind of understand the difference between going forward and then being caused to go in the reverse direction versus going forward, then stopping, then being forced to go in the opposite direction. It's more stages to that function. So the argument is that something gets hit by a force, the force is stuck on it, so it moves to a new position. When it at that position, it encounters the opposite force. Okay, so now it stops moving. Okay, the opposite forces, the forces reflect, so they leave. Okay, and now we just wait for a new force to hit it. So a new force hits it this way, then it moves this way. So the object, okay, goes from being moving, and then it stops, and then it can move in a new direction because a new bit hits it in a new direction, and then it stops because some bit hits it going this way, but it just stopped it. It didn't make it go that way. It just stopped it. And then the next force will hit it and make it go somewhere. And so it's all energy conservation. But the point is that physics didn't even consider these different ways of understanding motion. So clearly the argument is drag would be a real issue. And the way you overcome it is with the little wagon idea, the way of trapping energy. And that will allow you to trap momentum in a direction. So if I have two of these electrons, the understanding would be is that, like the cart, the energy will bounce back and forth. And whatever way it went in, like the cart, is the way it'll continue to travel. So it's always the first cause is the cause that remains. It's always a remainder. So it's like the beginning of a circle. A circle is zero, okay? But the truth is, this motion, the first push this way, all the rest of these cancel out. The one you never cancel out is this motion in an orbit, the initial motion. You never kill that. So it just keeps redoing the process because you can't get rid of the first cause. So the first cause is the first thing that hits the electron, right, in this example of where it's trapped. And so whichever way was the first cause, whichever way the force got trapped, whichever way it was going when it got trapped, reflecting, is the way the thing will keep going, because it'll keep going from, I'm going this way, and then I'm stopped by the equal and opposite force, drag, running into more force. So that's the idea, right? There's more force coming at you when you're moving into the fields, right? So when I move towards you, especially near the speed of light, I would get so much brighter. I move away from you, I get invisible. I'm so dim. So that's the real game that's happening when it comes to motion. Motion means you change your position. So now when you're moving into something, you reflect more to the world, the universe. When you're moving away from it, you reflect less to the universe. And that's the nature of creating frequency, or photons. You create photons by making a lot of stuff reflect, and then no stuff, very little stuff reflect. Okay, very few reflections, and then a lot of reflections, and then very few reflections. And so everything's doing that to the universe. And it takes more than one electron to create enough of this for us to call it a photon or something we can see, but that's what everything's doing. By changing its position, it's moving into a field, or it's moving away from this field, and it's moving towards this field. So obviously, right, it's going to reflect more of this field, and it's going to reflect less of this field. So this field is going to see something different than that field is going to see in terms of the energy coming off of it. And obviously you just don't need much motion then to be creating all kinds of frequencies in terms of what different perspectives will see. And it's all about what perspectives see. So it's like the magnet. If you look at the bottom end, you see one thing, the north side. If you look at the south end, you see something else. So where you're positioned based on which way something's moving is everything. So with this simple dynamic, you can explain everything. And again, so the drag is not dragging it. It's not killing the momentum. It's just causing the momentum to have to keep doing its little circular thing, which is it keeps have to doing its restart. It has to keep restarting. So that's what this energy would do in between. It would just keep restarting this motion. The universe would stop it with energy coming this way, right? And then it would reflect and restart it again. And then it would restart it again. And then restart it again. So, yeah. And obviously when it's moving this way, it's getting hit by less this way, so the energy travels further this way than it travels this way. That's all you're really doing, is changing the time it spends going one way versus the time it spends going the other way. But the initial motion can never be underdone. Can't be undone. The drag can't kill the initial motion. It just changes the shape of your circle, so to speak. Your circle just becomes some other shape. But it's the same energy, that restarts the circle when you get to zero, the complete trip. Yes, you've canceled, all this stuff cancels, all the little things cancel, except this. Go this way. That keeps going. So, all you do is just, like I said, if you thought of it in circles, you're just changing the shape of the wheel that's rolling. And if you think of it inside a box, you're just changing the amount of time the energy spends going one way versus the time the energy spends going the other way. But the fact is that you're just changing how far it travels per dash. So you change the frequency, but you don't change the fact that it's moving in a direction. And so that's basically how momentum is preserved in big objects like us, is there's a bunch of these little carts, and they're jerking in a direction, and they just keep jerking in that direction. Once the cart is made, the helium nucleus, the proton and 2 electrons, once you create this mechanism, well, 2 protons actually, this energy just keeps bouncing this way and pushing electrons this way and pushing protons this way. So these 2 motions don't kill each other. Going this way here with the proton doesn't undo the momentum this way created by these constant pushes. And so this mechanism ends up moving this way in net. because you changed the dimension in which the reflection took place, and that's what the inverse relationship between protons and electrons allows to happen. Instead of it being an opposite reaction, it's just moved into this other dimension. So the simple argument is you take a action and you're just saying the action comes in this way and the action leaves in this other dimension. So that's kind of obvious that conversion, could go in and out, so you can take a choice of either one of the other two dimensions. But the fact that that turn happens means that you didn't use up a piece of energy going this way to create that. And so you still have energy conservation in this direction. Better way to say that probably, but it's not. You change this, into this, and obviously the universe substantially changes when the reflections are going in the equal and opposite direction, and when they don't. Okay, the universe is a very different place. All right, so that's probably enough. Going through the basics. So some people say it's just, there's somewhere a whole bunch of evidence compiled that this doesn't work, and there is no evidence. Like I said, this is all part of the established physics in its elemental form. So if you go back to Maxwell and you go back to his mathematics, and especially Gauss, it's all based on straight lines. Okay, you want to find out why there's a curve somewhere. Well, you just find out what the straight lines are to make that curve. So again, I could use the magnet as an example. That all that really is happening is you're taking, two different polar objects, and you could just understand them as radiating. This was a red force, and we'll just try to draw in two colors so we'll make this the north side. That's not different enough. Let's try this color. Yeah, that's different enough. Okay, so the two sides are radiating something different. And all you're doing is measuring at different locations how much of this, how much of this pull stuff is hitting. So this was the north side of another magnet, and this was the south side. All you do is measure from the two sources. How much of this is hitting it, and how much of this is hitting it. And so if this was an electron, what would this short line plus this long line of the opposite force, so one's pulling, one's pushing, so to speak. One's creating an absence of push, and one's creating push. So you just measure that versus the same thing happening to the other one. So the same process is happening. It's getting hit by two different lines that are having its completely opposite effect. So this one has a net this, and this one has a net that, and it finds equilibrium. And so it bends to a certain position to line up with the field and create the field lines. But the lines, the places on this line, are all understood as straight line vectors. And I could go to the two-slit experiment and explain how that is likewise. Straight line vectors from locations are deciding the pattern. Okay, it's not being decided by anything curved or bent or crooked. Any crooked line, anything that looks like a wave, okay, is being created by straight lines of rays. Just like the sun's radiation can be understood that way, a light bulb can be understood as these straight lines, rays of light. Okay, and that works. It's mathematically coherent. Okay, the formulas and the rest of it like these straight lines, and it all can make sense, and you don't there's no confusion about anything going in these directions. These lines are just an emergent something that could be understood to exist. They aren't elemental. The elemental is where the straight line vectors add up to, and the whole thing can be understood. Every curved line can be understood as a combination of straight line vectors, you can draw the lines of force. And those, not field lines, the lines of force will tell you what's causing the effect. The field lines are just an emergent byproduct of what the lines of force are doing. And that's deeply Maxwellian and Faraday-ish. The problem is they thought the emergent lines were pathways, and they're not. They're just byproducts. All right, that's enough. So this is still the old simulation. We have to redo the simulation with the new functions, the simpler function. The good news is it's simpler, so it shouldn't be too much of a problem. Bad news is people have lives and they can only have so much spare time to work on it. So anyway, we'll get there eventually. So yes, I guess I'll have to actually put a comment on a Piro video, and we'll just see about wasting. I mean, it's not a big deal, right? I can throw away an hour, you know. But we'll see. About trying to have some interrogating why physics doesn't accept these simple rules, simple premises that are sort of just indestructible as something that makes the world go round. Well, it's straight lines, it's indestructible force, and it's matter that's completely owned by the force. It does exactly what the forces tell it to do and nothing else. It doesn't have any matter or mind of its own. The force clearly tells the matter what to do. And as a consequence, the world the force lives in is different because the matter's in a new position. And that's all there is. Not complicated. No woo needed. No entanglements, no 400 fields, no antiparticles, none of that stuff is necessary. I mean, if you want an explanation for antiparticles and all the rest of these silly things, they're just the idea that, you know, you can create an environment where little bits keep hitting something. So if an electron's moving through an accelerator or a proton, it's moving because you're hitting it with a bunch of energy. You're hitting it with a bunch of X-rays and gamma rays and you know, even heat, all kinds of radiation, and that radiation is moving the speed of light. I mean, infrared light moves the speed of light. Okay, so even though it's weak light, it's still an invisible force that will move something. Obviously, it'll move an electron, and that's the whole point, is that the thing itself is not moving. The force keeps pushing it, and you've got more pushes behind it than you have in front of it, and therefore it's going to keep moving. All right. But anyway, so I mean, what they're defining is like a muon, for example, pretty much decays into 2 electrons. I mean, frankly, it's just 2 electrons that are being pushed, like 2 cars drafting in a car race, and so it avoids drag, you know, because there's the one behind can't see the impacts that are happening to the one in front, so it essentially just keeps getting closer and closer to the other electron, creating more and more pressure to compensate for the drag. And so the closer the one car, like the back car is getting pushed, right? The front car is getting hit by the drag. But the trick is, as the two of them get closer and closer together, they create an infinite amount of energy between them, potentially infinite, you know, in terms of Planck distance infinite. A 10 to the 50th kind of amount of force they can create between them by just increasing the number of impacts between them. So as the electrons get closer, incredible pressure builds up, but still this electron, okay, the force is still hitting it, so it just pushes both of them. But anyway, so the cart keeps moving. But obviously they have to push against the drag, right? The drag is real, and that's why when they accelerate particles, they have to put intense amounts of energy in to move these tiny little things. Why? Because the faster you move them, the more drag they're running into, and the more you have to overcome the drag, the more energy you need to keep pushing against the drag. That's why they need all of that electricity just to move tiny, tiny, tiny mass of particles, right? Mass so small you couldn't feel it in your hand, and yet it takes gigavolts and gigaamps, gigawatts of electricity to move something you couldn't even feel its weight. It's so light. And why are they having such a problem? Well, yeah, because they're moving it against drag. All right, anyway, so enough of a video. Till the next time and such. So we'll see what happens. Such. Some kind of rational links to some rational counter argument would be interesting. Some argument defending why there's no way a rational person doesn't believe in bent space and entanglement and photons being bent twice as much by gravity and some sort of thing called the time dimension. Woo. Yeah. Some evidence that there's just no way not to believe. There's so much evidence proving. Show me the proof. And I'll show how it's weak and in some cases completely irrational. All right. Inconsistent with the actual evidence. Come on. Why aren't you working? Do your little job here. Okay, there we go. So, till the next time and such.